Welcome to this 10th episode of the Verilog Bench. Today we're going to be looking at the origins of multi-layer AHB. This video has a scope guardrail. DVI0045 is a technical overview, not a full normative bus protocol specification. So this video explains why multi-layer AHB exists and how the topology is organized. It does not replace the later AHB protocol videos that go signal by signal. The date context matters here too. The front matter shows issue A in March 2001 and issue B in May 2004. Those are the dates that place this architecture step in the AMBA story. Later public distribution records should not be mistaken for the point when multi-layer AHB was introduced. The problem statement is straightforward. As the number of masters grows, one shared AHB path becomes a bandwidth bottleneck. Multi-layer AHB addresses that by using an interconnect matrix to create parallel access paths, while still reusing standard AHB masters and slaves wherever possible. The core architectural idea is simple enough to sketch in one picture. Each master gets its own layer into an interconnect matrix. The matrix routes the request to the target slave. If two masters are going to different slaves, the transfers can proceed in parallel. That is why this is an interconnect architecture rather than a new bus protocol. The implementation model is also clean. Each layer decodes the destination. The matrix muxes the request to the appropriate slave port. If two layers target the same slave, arbitration happens there at the point of collision instead of forcing the whole system through one shared decision point. When two layers want the same slave, one wins and one waits. The document explicitly notes that the waiting layer is held with HREADY, and that an input stage stores the pipelined address and control information until the access can continue. That is a useful architectural clue because it tells you where buffering and arbitration state belong. The advanced options section is really a pattern library. You can make slaves private to a layer, group several small slaves behind one port, place multiple low bandwidth masters on one layer, split the system into subsystems, or build multi-port slaves for high-value targets like memory controllers. So the matrix is flexible by design. The worked example in section 1.4 is useful because it mixes these ideas in one design. One CPU has a dedicated layer. Another CPU shares a layer with DMA. Some memory is private, while shared resources sit behind a matrix. The example also shows an AHB to APB bridge and a dual-ported memory interface, which makes the bandwidth argument concrete. The decision rule is pragmatic. Use multi-layer AHB when real contention exists and the extra architecture buys meaningful parallelism. Do not use it just because it sounds more advanced. The benefit is bandwidth and topology flexibility. The cost is matrix logic, arbitration, and buffering. The architectural takeaway is that multi-layer AHB scales the topology rather than redefining the bus. Its origin is in the 2001 and 2004 document issues. The matrix enables parallel access, but it still relies on familiar AHB building blocks and semantics. If this architecture overview was useful, like and subscribe to be notified of future videos. Later in the series, we return to the AHB branch for full protocol history and signal-level detail, keeping this topology view clearly separate from the bus rule walkthroughs. To close, here's a short glossary for the core terms in this video. AHB means Advanced High Performance Bus. APB means Advanced Peripheral Bus. DMA means Direct Memory Access. And SoC means System on Chip. CPU means Central Processing Unit, one of the masters shown in the worked example system. HREADY is the AHB signal that shows whether a transfer can complete, which is why the document uses it when describing how a losing layer is stalled during contention.